Hi guys, I'm sorry for the long time without videos. I had to deal with some issues back at home, back at work. I had a full plate of things to worry about, but now I'm finally free for to focus on the videos again, and to try to make up for the lost time. I'm gonna try. I'm gonna do my best to do 2 videos a day to see if we can go over all the material within this week, maybe, or maybe at most next week. But for now, um, today's videos, the first one is gonna be this one. It's gonna be all about functional programming and what it means and what do you get from that. And we're gonna talk a little bit about universal quantification too. So, oh, forgot about that. So anyway, right up to now we have seen functional programming, or really we really haven't seen anything that is really purely about functional programming. I mean, we have seen pattern matching, which is often associated with functional programming languages, even though it's not necessary. I mean, for instance, Clojure, which is another Lisp language, it is functional, but it has no pattern matching, at least natively. So it's a feature that, yeah, it's often associated with functional programming languages, but it's not functional programming per se. So up till now, we have seen something that is more like imperative programming. I mean, everything that we have written so far, we could have written in something like C or Java or Python. We really didn't need functional programming for that. I mean, it's just functions working with numbers, right? And in the case of Power, here working with tuples containing numbers. Well, right now we're going to see more of what functional programming means. Now, well, give me just a moment. I don't know if you were hearing that noise. Anyway, so up till now, as I mentioned, we have seen only things that are more procedural in nature. But what does functional programming give us that other paradigms don't give us? What makes functional programming special? And I think that there is like one base thing that it's the minimum you need to get to have a functional programming language. But in a good functional programming language, you're going to have a few extra things. So we're going to talk about those. So the first thing that you need, and the most important, is that in a functional programming language, functions are everything. Functions are your main form of abstraction. It's kind of like in an object-oriented programming language, classes are your main form of abstraction. And maybe if you come from a prototype-based object system, then prototypes and objects are just going to be your base thing. But in the case of functional programming, functions are the most important thing. It's what we use not just for writing our code and the process that we need, but also the abstractions that we compose to create bigger things out of that. And in future episodes, we're gonna see how functions can be used to make some pretty powerful abstractions. But for now, let's go with the basics. So we have defined functions here before, factorial and power, and I have even shown you how it desugars into lambda expressions, which are the things you use to make functions themselves. But that's as far as we have gone, and you can say, hey, I can make methods in an object-oriented programming language. What's the big deal with functions? It seems like it's just a way to package code in one place and that's it. Well, the thing about functions in functional programming is that they are what is called first-class objects, which means that they are things in and out of themselves. You can move them around, you can store them in variables, which is what you do when you define something. When I make this definition, I'm creating a def global variable that contains a function, that is the factorial function. But also I could put a function within a local variable. I could have a data structure that contains functions. I can make functions on the fly. I can do all kinds of things with my functions. And one of the beautiful things about this is that I can use functions then to encapsulate patterns that I can reuse and that might have holes in them, things that need to be filled out, details that are not known at the beginning. So I'm gonna show you an example of how that works, how that looks like, by trying to do something that we haven't done so far. So right now, here is this program that just prints hello world. What if instead we made a program that took the arguments from the command line and then told us maybe the number of elements, the number of characters on each word that we get? So what would that look like? Well, we're gonna need something like some function that, given the arguments, just gets the number of elements of each, and it just gives us back a list. Oops, forget about that. And it just gives us back a list containing all the numbers, all the sizes. So let's do something like that. Okay, so def word sizes takes a bunch of words, and it's a function that if you give me a list of text, I'm gonna give back a list of ints, which are gonna be the sizes. So I'm gonna do some pattern matching on these words. If it's empty, give it back empty. Otherwise, if there are some words, then I'm gonna call this recursively on the rest, and here I'm going to use the function text size, which comes from the text module. This gives me a size of a piece of text, in this case a word. So here we have this, really nice, and we can use this on all of the arguments that we're gonna get from the command line. Now this code here is not gonna work because log expects text, and we're giving it back a list of ints. It's not gonna work. So instead of saying we're gonna give back a list of ints, let's get it back another list of text. So we're gonna turn the sizes back into text. So we're gonna be using the show function, which we got from the int show structure over here, and it's gonna take the number that comes from text size back into text. But this time it's gonna be the text of the count of the size. And since this is still going to be a list of text and we need just a normal piece of text, we're going to join them using the join with function. Also from the text module, we're going to join them with spaces and commas. Simple as that. So this should compile. Let's see if that is true. And right now this is still not very functional in nature. We're still not doing anything special with our functions, but we're gonna be refactoring this so you can see the magic of functional programming in action. But right now let's just go with the simplest possible way of doing this, which is this one, and then we will see how to make this into a more functional program. So let's just wait for this to compile. Probably taking a little bit longer because of the recording. It's finished. Let's just wait for the compiler program to exit. It's done, and hello world 5. Hello has 5 letters. World also has 5 letters, and indeed our word size program works. So what can we do to make this more functional? Well, I previously talked about how to use functions as the means of abstraction and using them to have these algorithms that have holes in them that you fill. Well, we have seen, this is a nice, with this function, we have to go over the list that we get and build a list of the results that we are needing. But if you really think about it, that is a problem that happens quite a lot. Something that happens very often, It's very often even in languages that are not functional. I mean, everybody has written a for loop at some point in some programming language. Going over sequences of things, very common thing. So, is there any way that functional programming can help us abstract that away? Well, it's kind of problematic if you really think about it, because every time we go over a list of things, we're always doing something different. I mean, in this particular case, we're getting the sizes of words, but we could have done anything other than that, Going over a list and doing something on that is a very common thing, and it's always different. So if you really think about it, it sounds like impossible to have like an abstraction that just goes over the list. I mean, think about it. In normal programming languages, in object-oriented or imperative programming languages, people always have to write the for loops all over again. There's no way to abstract it. It's kind of annoying. Well, actually, it is possible to abstract this in a object-oriented programming in a functional programming language. It's actually very easy to do it, in fact. So we're actually gonna do it right now. So instead of relying on our word sizes function for doing our iteration and the transformation, we're gonna make a function that only does iteration, and we're gonna leave the transformation to other things. So we're gonna make this function, and this is not the name that you usually find it with. This is not the name in which you usually find it on functional programming languages, but this is gonna be the name for now. And later on, I'm gonna introduce the real name that people tend to give to this function. But for right now, let's call this function list iterate. And list iterate takes a list of things, and we call it xs as many x, x plural x's, and we're gonna over x's, and here we have an x's prime, an x's, and we're gonna do something to x, and we're gonna keep on iterating on the rest of the list. Simple as that. And if it's empty, we give you back an empty list, and if it's not empty, when we build something that is transformation of an individual element and recursion over the rest of the list. Now, we really don't know what to do here for this thing, because this is just an algorithm for iterating over a list and doing something, but the something is kind of unspecified. But this here is where functional programming starts becoming relevant, because in the same way that we can receive the list of things on which to work as an argument to our list iterate function, we can also receive the thing to do, the operation, and it's gonna be a function. And we're gonna call it f for function, and the transformation on each particular element in the list is just applying the f function to the element, and that's it. And of course, in our iteration, in our recursive call, we're gonna put f2, so in each call we always apply the same operation. Now, this is really interesting, because here we're seeing the power of having functions as first-class things. Now we can write a pattern of iterating over a list as a function, and you can do anything you want on lists. It doesn't matter what operation you want, you can always do it, and you don't have to worry about the iteration, because the iteration has already been abstracted away in one function. You write it once, and you reuse it everywhere. It's kind of like being able to write for loops in object-oriented or imperative languages without having to go through all that hassle of having to make a new counter variable and having to increment it on each step. And everybody knows the drill. Bar I equals 0, I mine I less than the size of the array, I plus plus. Everybody knows the drill. It's boring, it's tiresome to do. With this, I don't need to do it. And with this, I can just simply replace this word sizes thingy with something like, first I'm gonna iterate over the arguments and get the count, get the sizes, and then I can just iterate again and transform those back into text with the show function. And that's it, and I can just forget about this. Completely unnecessary. It's really nice. It's really, really nice. I mean, it's kind of a bit more nested now, but you know, there are ways to deal with that. It's actually pretty simple. I'm gonna show it to you in a moment. But you might wonder, you know, what is the type of this function? Because so far we haven't typed it. It's kind of weird, you know. I mean, what would be the type of something like this? Because this algorithm has to be very general. I mean, we could make it so it always works with text or ints, and it will work perfectly. But again, you know, you can do iteration over lists in many, many scenarios. So you wouldn't want to constrain things so much. So how would you do it? Well, now I'm going to explain what universal quantification does and what it's all about. So up to now we have seen types that are very concrete. The type is very precise, it tells you everything there is. You know, here's a function of one int to another int. Here is a function of two ints in a tuple to another int. Well, with universal quantification you can introduce what are called type variables, which are types that are kind of undefined. It's kind of like a way of saying, hey, for some type, this function works this way. I don't care what type it is. I'm going to write my functions in such a way that I don't care about the type, but by having these type variables, my function can work with any type, provided that, you know, certain rules are kept. So how will this work? Well, for that you use the all macro, which stands for all, as in for all variables A, B, C, whatever, this is a type. It's called universal quantification in a more mathematical way, but you tend to see it as for all. There is actually even a mathematical symbol, which is an inverted A, but of course we're not going to write it here because it would like a little bit weird. So, you know, we know that our list has to be of something, but it has to be general. So there is one variable for the list. But our function could transform the types of the things that we receive in the list, if you really think about it. Like here, we would take a list of text, would we transform each particular text element into an int element. So we can transform types from one type to another. So here we're actually going to need two type variables. We're going to call them A and B. The names could be anything, even things that are not necessarily one letter. But, you know, we're going to stick to simple things for now. And this is a function. And the first argument here is another function. And it takes an A and returns a B. And if you give me a list of A's, I'm going to give you back a list of B's. So this might look a little bit weird, but let's explain it. So I'm going to be receiving two types. I don't know what they are. It's going to depend on the circumstances. Here it might be text and int, while here, well, it's also text and int, but in the opposite order. You know, I get a list of ints and I have to return a list of text in this particular place. So there are two types. I'm going to receive a function that can transform things from the input type to the output type, which is this here. This is the type, and that's the type of the f function. Then I'm going to have a list of inputs of the input type, which is A. This is my x's here, and I'm going to transform it into a list of the output type by transforming everything using f. So this is the type signature for the list iterate function. And we're going to try it out. We're going to see if it works just the same. So first, let's compile this. And it works perfectly, compiled perfectly. And when I run it, does this work? It does. It does work, as it turns out. So the count was perfect, and it worked perfectly. You know, thanks to universal quantification, or, you know, for all, or just the all macro, however you want to see it. Now, this looks a little bit funny, you know, this looks a little bit ugly. Can we clean this up, before, wrapping things up in this video? Well, there are some ways. I'm going to show you some nice tricks. So one way which we can clean this up is by fusing these two functions together and just doing one list iteration. So this here is a function. It's the function composition function. I know it looks kind of weird because it's a dot, but the reason is that in mathematics, function composition tends to be done with a symbol that looks like a little circle. And since I cannot have that symbol in here, unless I use an O, which is gonna look kind of funny, I use a dot instead. It's a simple way of doing it. So with this, I can fuse these two functions, and it kind of works like this. If I have a function f and a function g, then uniting these two is the same as lambda of x f g x. So basically, I'm going to be applying this function first, and the output of that is going to be the input for this function. So first, I'm going to get the size, then I'm going to transform it back into text, and that's what I'm going to be doing with the iteration. Kind of what we were doing previously with our word sizes function. So again, this should compile with no problems. And it does perfectly. And again, does this still work? Well, yes, it does. What do you know? And there's another way of doing this, which I personally like for the things that are very nested, because you can only go so far with iteration. But I can do something kind of like this. Well, first, let's go back to the original definition. And I'm going to show you a nice little macro. It's called the piping macro. I don't remember if I showed it to you guys on a previous episode, because it's been a little while. Maybe I didn't, maybe I did, I don't know. But first, let's compile it down, and then I'm going to explain it. Then I'm going to explain how it works. Compiles using piping now. Perfect. So how does this work? Well, the piping macro is great for when you need to apply a bunch of functions consecutively. And what it does is that, it takes the expression that you start with, and then it pipes it at the end of the next expression. And then it does that recursively until you have a completely nested structure. So what this does is kind of like this. First, it puts this in here, gets rid of this, and then recursively puts this in here, and then we're out, and then we end up with what we had down here. But as you can see, this is way easier to write, way easier to maintain, way easier to add new steps or to remove them without having to deal with the nesting, and it's much easier. It's one of the tools that, as you become a more proficient Lux programmer, is going to become one of your go-to tools for day-to-day programming. So let's stay with this particular definition. It looks kind of nice. So we have seen, the power of functional programming by being able to pass functions around from function to function. We can write functions that receive other functions and do stuff with them, and use that functionality to encapsulate very common patterns everywhere, without having to worry about the details of, how do I work with this particular piece of data or whatever. And that's really powerful. And, we have also seen, how universal quantification can allow you to write algorithms that are incredibly flexible when it comes to the types of the things on which you work. And finally, before I conclude this video, I'm going to talk very briefly about another aspect of functional programming that we're going to be seeing more in future episodes, especially when we start talking about concurrency and other things, and that is immutability. You see, you don't need to have immutability for your language to be functional. Like, for instance, you could argue that JavaScript is functional because you have functions. It is true, even though it's all data is is pretty imperative, it's pretty mutable. But for a language to be more what some people would call purely functional, immutability is a very key aspect. So immutability is the idea, and again, I don't know if I mentioned this in a previous episode because it's been like 3 weeks. Sorry about that. But immutability is the idea that data doesn't change. Once you make a piece of data, you cannot change it. You can make new versions of the data which are gonna be different and independent, but you cannot change the original. So it's kind of like consider you have a variable that contains the number 5, and you decide to add 3 to 5, which will give you 8. Well, when you do that, you generate a new number, but you're not changing the original 5. It's not like now, in all the places in your program where there was a 5, there is now going to be an 8. So that's not going to happen. Because if it did, that would be pretty problematic. I mean, just imagine causing all kinds of bugs just by doing arithmetic. It would be crazy. Well, you cannot change the thing itself. You cannot change the number. If you have variables in some programming language, you might change a variable that contains the number, but you cannot change the number itself. And in Java, you also have something like that for strings. You can create new strings based on old ones, but you cannot modify the old strings, right? So again, you can also have like a variable that contains a string, and you can update the value of the variable, but you cannot change the string itself. And if you really think about it, changing the string will be kind of funny. Like for instance, let's say you have a UI, in Swing or some other framework for Java, and you put the label of some form as the username label. It contains the word username, and the word username came from some string. Now let's say that Java strings are mutable, and you change the string username, and now it says ID. Well, you wouldn't want changing that string to immediately change the UI. You would like to have a more formal process for changing the label of the UI, because I don't know, maybe you're using the string in some little way and you don't want things to happen in one place to affect your UI code in ways that you were not suspecting. So immutability allows a certain measure of isolation between the processes that use data by not allowing changes to data that happen in one place to immediately affect the other place. So if you want the other place to be affected, you have to go through a more formal process for propagating the change, instead of the change happening automatically because you change some variable or you could change some object. Now you might think that's a very simple thing, but in reality, considering that most programming languages have mutable data types, it can be pretty easy to get some kind of contamination between processes when one changes that data structure that the other one is relying on. And that happens especially when you're talking about concurrency, and when you're talking about different processes running concurrently and having access to shared data structures. Then it's especially likely that you're gonna end up with some kind of corruption, some kind of problem. I have an anecdote from back in college. I was given this exercise by a teacher, and we were supposed to make a program that goes over a maze. And whenever we reached an intersection, we had to spawn 2 other processes and go over the maze in those 2 ways, simultaneously. And they could keep on multiplying depending on what other intersections they found. And I made my program using Clojure, which is a functional programming language. And a friend of mine did it in Java. And what happened was that, I wrote my program completely sequentially, no parallelism. And then I tested it, and it ran perfectly. And then what I did was that I replaced the function that I was using for sequentially going over all the routes to do it in parallel. And I didn't change anything else. I only changed the function. And then the change was so small that it only constituted 1 letter. The sequential function was called map, and the parallel version was called pmap. So I changed 1 letter, and I had a parallel algorithm that worked perfectly. My friend, on the other hand, had all kinds of trouble because he had all kinds of weird corruption because he was using an array to manage, the path information for the agents moving in the maze. I had all kinds of corruption with some process modifying the memory that the other process was using and destroying, any kind of information that it needed. And he got all kinds of trouble with that. And then, the teacher kind of advised him, hey, you should maybe do a deep copy of your array to have like a separate array so that your processes don't step on each other's foot. But I didn't have to do any of those things, because I was using immutable data structures in which every time I made a change, it was independent of other data structures. So my data structures were always independent. One process could never interfere with the other one. But he was using arrays which were mutable. So every change to the array made by one process completely messed up all the other processes that also depended on the same data. So functional programming may seem very weird because it has all these ideas that you don't find anywhere else, and it seems so counterintuitive. Like some of you guys might think, but wait, isn't immutable data structures inefficient? I mean, you have to create new things instead of reusing them. But all of those things can be addressed, and in functional programming can be made really fast and really efficient. But most important of all, it is in many ways safer, which provides a much more productive programming experience, because the less bugs you have, the less time you gotta waste bug hunting. So functional programming is a great asset to programmers. So we're gonna leave this video up to this point. If you remember from last video, I mentioned that we were going to cover other topics in this one, which we didn't, but it's okay, because I'm going to make another video also for today with those topics. So for now, this was the class, Functional Programming, Immutability, Universal Quantification. Next class, we're going to talk about signatures, structures, and monads. So see you then.